Hi everybody. So for this devlog, I decided to work on a graphics update, and you can see this is an example of what it used to look like. You see there's problems with the lighting, for example, as the model rotates. The model is also made up of quads, which I ended up triangulating later. The terrain's not shaded. There's also an issue with the aspect ratio, among other things, and here's what it looks like now. And I'm starting to like the way it looks. I mean, there's still a lot of room for improvement, as I'm still not an artist. I'm mostly focusing on the systems, but yeah, definitely a bit easier to look at. The bulk of the work was actually with these shadows, which I'll go into a bit more detail here in a minute. Also for fun, I tried a few different types of shading. This is cell shading, which didn't really look too good. And this is rim shading, which kind of was cool. Maybe could be useful for something in the future. Not sure. With the lighting implementation, there was one thing that kind of irked me a little bit, and it's this inverse in the vertex shader. Generally, you can compute this on the CPU, but because of this skin matrix here, which is used for the animations, I have to compute it per vertex, which yeah, just has a kind of a bad smell to it. So maybe in the future I can fix that, but for now, I'm just going to leave it. So when I started thinking about implementing shadows, I didn't think it would be too complex or too time consuming, given what I had already known. And arguably for a single shadow map would be the case. However, the devil's really in the details when it comes to providing shadow for a larger area. So conceptually, this was my understanding. Let's assume we're rendering a character facing the camera. And as we know, we have this MVP, and these are a set of transforms. In this case, the important ones are the V and the P. And the V is used loosely to align the scene with the camera. And P is for your projection. So either orthographic or perspective. And yeah, if it's perspective, it has perspective, and also deals with the clipping planes. So if we want to create a depth map, which is one of the steps in the shadow mapping process, we need to render the scene not from the camera's perspective, which is here, but from the light's perspective. So let's say I draw the sun in the same way that my children would draw the sun, and it has light coming this way. Actually, it has light going all directions, but since the sun is considered to be very far away, you can actually treat these lights as being parallel, which is nice because you can use an orthographic projection, so you don't have to deal with some of the perspective when you're doing the calculations, which is nice. So the difference is, if we're rendering from the sun's perspective, and we're only rendering into a depth map, by the way, so only depth values, we still need the M, but now you need an LV and an LP. So the light's view and the light's projection matrix, which is, we already said was ortho, right? So from this, we'll end up with a depth map that looks something like, I'll just keep it yellow here, something like this. I've got the nose and the eye. And when it's time to finally actually use this depth map, to do the sampling, what we do is when we actually go to render the scene, let's say we're rendering this wall, when we get to a fragment on the wall, we'll actually use another transform to put it into this shadow map space, and then we can test, and actually there's a nice little test OpenGeo has using a shadow sampler. We can test if it's in or out of shadow. So in this example, this would be in shadow. So overall, not overly complex. However, if you end up with an area that's quite large, you'll end up with significant undersampling, which this is what it looks like. This is without the filter. And if we add the filtering to it, this is what it looks like. This happens because I have too many fragments mapping to too few shadow textiles. After understanding it conceptually, here is the first depth map. It doesn't have any animation information. And here is it with the animation information. Once I realized that the single shadow map was not going to have enough resolution for the amount of area I wanted to cover with shadow, I started looking at cascading shadow maps or cascaded shadow maps, whichever way, and I ended up landing on the NVIDIA paper that I have in the description for parallel split shadow maps. So the general idea is, imagine you have a frustum like this, you have a near and a far plane, and take note that the viewing area, this frustum here, is much smaller than the total space of the world. The idea is, instead of one shadow map, we're going to create multiple shadow maps to sample from. So you might have one here, maybe you have another one here, I don't know, another one here, something like this. So the idea of the NVIDIA paper is deciding where to actually pick the splitting points of these. That's over here. So they have a couple different schemes. they have a uniform scheme and a logarithmic scheme, and they combine those with this handy little equation here. They combine those in a way to improve the overall sampling. However, in my case, the lambda that I picked was 0.9. So really I'm leaning more into the logarithmic scheme because I value higher resolution closer to the player. But anyway, the code for that looks like this here. And the video paper also touches on a couple other concepts. One of the things that it was sort of missing was one of the problems that I ran into. And the issue is, and I'll show it in a second in a video, but the issue is, as the camera rotates around, the bounding boxes, which are axis aligned to this coordinate system, they will actually not be square. So in some cases they'll be square, but as it rotates, the shape will change. And this causes warping and artifacts, as you can see here. And the code to fix this is pretty simple. It's this right here. Basically, I couldn't use the crop matrix that they provided in the paper. Just setting my own orthographic projection, but calculating the extents of each slice. So basically making them square, and that gets rid of the warping. In the paper, there's a bunch of other cool stuff and implementation details, and they do talk about this bounding box and what coordinate spaces it should be in, and that is helpful. Again, they don't talk about the rotational issue, but essentially what I do is the split that comes in from the PSSM algorithm, it basically is, it's in world space, and then you can calculate, using a little trigonometry, you can calculate the 8 points that make up this part of the segment of the frustum. I only have 4 circles here because it's in 2 dimensions, but in those 8 points, you can then transform them into this coordinate space and then do your typical bounding box operation on it to come up with the maps. And as I mentioned before, using the extents to make it square. And that seemed to work for me. The final thing to do was add the soft shadow edges, which, although we had an improvement in the shadow map resolution, there's still a hard line between things that are in shadow and out of shadow. And that line was kind of aliased a bit and didn't look super good. And this is considering that I get a 2x2 PCF filter for free from the hardware. It still wasn't really enough. So looking around at my options, I ran into this paper here. And this is a really cool idea. It's basically creating your own PCF filter with some noise built in and being able to sample in an efficient way by converting the filter grid into a set of rings and only testing the outer ring. So if you look, this filter here, basically they call it a regular grid, but they jitter it, which you can see the code. That's what this is doing here. This returns a value between 0 and 1, and then they warp it using these equations up here. And the interesting part in the paper, they talk about storing the data in reverse. This is sort of the efficiency part because each row of the filter actually turns into an outer band. So if we do it in reverse, let's say the filter is 8 by 8. So the first 8 would give me, the first row would be 7, which if you look where y is used, it's down here. Even if we normalize it, y will end up being quite large, which if you look where v is used, it's square rooted, which will actually control the distance. So the first row of 7 will actually end up with a larger value, pushing it to the outer bands, which is pretty cool. So when you actually do the sampling, you don't need to sample all, for example, 64 values if we're doing 8 by 8. You just need to sample the first band, if that makes sense. And one thing I noticed, if you look over this example, I still see some aliasing. So because this is a disk, you can actually spread out the sampling a bit more, and you can kind of play with that. But spreading it out a little bit actually removed, for example, this artifact, which doesn't look terrible, but yeah, you can still kind of see the aliasing a bit. So spreading it out ended up being a bit more smooth. But anyways, this was the final thing. Thank you for watching. Next devlog, I'll probably be working on gameplay. Take care. Bye.